It's going to talk about not concordance and homology spheres.
Thanks for the introduction, for the invitation to speak here. I've enjoyed the conference so far. Great, so I'll be talking about not concordance and homology spheres, and this is joint work with Adam Levine and Ty Lidman. So let me start by reminding you what the not concordance group is. So the not concordance group, we look at knots. We look at knots in S3 under connected sum, and we mod out by the equivalence relation of concordance, where two knots are concordant if they, if K1 and K2 co-bound a smooth, properly embedded cylinder in S3 class I. Right, so the picture is you have S3 class 1, S3 class 0. You have your knot K2 sitting in here, and there's some cylinder connecting K1 and K2. And so the identity is generated by what are called slice knots. So knot K is slice if it's concordant to the unknot, or equivalently, if K bounds a smooth disk in B4, where you think of S3 as being the boundary of this 4-ball. And notice that it's important to have the word smooth here. If you didn't have some requirement on the disk, if you just required it to topologically be a disk, well, every knot bounds a disk in the 4-ball. You can just cone off. So note, every knot in the 3-sphere bounds a PL disk in the 4-ball, since the cone of S3K is B4, comma, disk. So today we're going to think of a generalization of the not concordance group. So first, I guess, Matt talked about homology cobordism this morning, so let me just remind you what the definition is. So Y1 and Y2 are homology cobordant if there exists a smooth, compact 4-manifold X with boundary Y1 disjoint union negative Y2, such that the map induced by inclusion is an isomorphism on homology. Okay, and maybe it's worth pointing out, right, so a manifold is homology cobordant to S3, well, if and only if it bounds a homology ball, right? If it's homology cobordant to S3, well, you just cap that off with a ball, and then in the other direction, well, you can just take out a ball. So something is homology concordant to S3 if and only if Y bounds integer homology ball. Okay, so what is our generalization of the not concordance group going to be? Well, we're going to think about knots in integer homology spheres. Instead of looking at concordances in S3 cross I, we're going to look at concordances in homology cobordisms. So in particular, since we want to be able to relate this to the ordinary concordance group, we're going to restrict our ambient manifold to being an integer homology sphere that's homology cobordant to S3, equivalently bound to homology ball, and then our equivalent relation will be concordances in homology cobordisms. So we'll denote this group CZ. So it's generated by knots in integer homology spheres that bound integer homology balls. And then we're modding out by this new sort of concordance where K1 and Y1 is sort of integer homology concordant to K2 and Y2 if K1 and K2 co-bound a smooth, properly embedded cylinder in a homology cobordism between Y1 and Y2. So the picture, maybe you have some homology cobordism X between Y2 and Y1. And then sitting inside there, you have some cylinder between your knots. Great. So I may forget to say it, but from now on, we'll just be considering integer homology spheres that bound integer homology balls. And great, so the identity in this group are things that are integer homology concordant to the unknot in S3, and equivalently, so that's equivalent to bounding a smooth disk in an integer homology ball. So K in Y is the identity, or trivial, in this group if K bounds a smooth disk in an integer homology ball. So if you're like me and you're used to thinking about knots in S3, well, one important thing to notice about now that you're in this group, well, when you take the connected sum, you have to also take the connected sum of the ambient manifold. So it's worth pointing out that, well, the connect sum of two knots, you take the connect sum of the ambient spaces, and then the connect sum of the knots. Any questions so far? Okay, so there's a natural map from the usual concordance group to this group. We'll call it B, from C to CZ. So you could ask lots of questions about this map. So an open question is whether this map is injective or not. One remark about this, so you could do the same construction, but replace the integers with the rationals. So instead look at rational homology cobordism. So if you do that, well, you can get a map from C to CQ, and this map is known to be not injective. So this is not injective. So for example, the figure 8, well, it's not sliced in the ordinary concordance group, but this bounds a disk in a rational homology ball. Okay. So we want to understand how far is this thing from an isomorphism. We don't know whether it's injective or not. You could also ask, is it surjective? And Adam Levine answered that question in the negative. So he gave a particular example. So let me tell you what the example is, or show you. So if you do zero surgery along both of these white components and look at the image of K in that manifold, so K in Y, right, so Y is the boundary, you can check Y is the boundary of an integer homology ball. Well, Adam showed that this not K in Y is not, so it's not concordant to any knot in S3. So in particular, it's not in the image of phi. So it's worth pointing out that being concordant to a knot in S3 is equivalent to bounding a piecewise linear disk in a homology ball, right? If you're concordant to a knot in S3, we'll just cone off the S3. That gives you a piecewise linear disk. And in the other direction, if you have a PL disk, the singularities are a finite number of cone points. So just sort of chew them together and remove a neighborhood. And that gives you a concordance to a knot in S3. So this is equivalent to the fact that K does not bound a PL disk in any bounding homology ball. Okay, so this is sort of a key difference between knots in S3 and knots in arbitrary integer homology spheres. So, great. So Adam showed that this map is not surjective, and we'd like to understand, well, how far from surjective is it? So we want to. That's sort of going to help us understand the difference between C and CZ. So the goal for today is to try to understand the difference between, I guess, phi of C and CZ, or in other words, we want to understand the quotient, CZ mod C of C. Great. So we have lots of knot invariants, we have lots of concordance invariants. Most concordance invariants, you can generalize them to knots in arbitrary integer homology spheres. That's not so hard. But if you want a concordance invariant that's going to descend to this quotient, well, what do you need to be true about your concordance invariant? It needs to vanish for all knots of S3. And typically, when we define knot invariance, that's not a desired property. So there's a real lack of invariance for understanding this quotient. Lack of invariance. So for a concordance invariant for knots in an integer homology sphere to descend to this quotient, you need it to vanish for all knots in S3, and that's typically not a desired property. Nevertheless, we're able to say something about this quotient. In particular, we're able to say this quotient is infinite. It contains a copy of the integers as a subgroup. So that's the theorem I want to tell you about today. So this quotient is infinite. In particular, Z sits inside this quotient as a subgroup. Great. So I pointed out that there's sort of a lack of invariance of concordance invariance on this quotient. So what invariants do we use? Well, we use invariants coming from knot floor homology. And in particular, we use two invariants together that allow us to understand this quotient. So we use some concordance invariants from knot floor homology, which is defined by Algebroth and Szabo and independently by Jake Rasmussen. So in its most general form, knot floor homology, right, to a knot K, we associate this thing called CFK infinity of K, which I guess Cyprian briefly mentioned. So what sort of object is this? You can think of this as a Z plus Z filtered chain complex. Over, well, we can work with the two coefficients. Wait. And so this chain complex is an invariant of the isotopy class of your knot, but within this bifiltered chain complex, there is some useful concordance invariance. So the first invariant that we use is the Algebroth-Szabo tau invariant. So tau is a surjective homomorphism from the concordance group to the integers. This is surjective homomorphism. So what is this invariant? Well, right, so this is a Z plus Z filtered chain complex. You can essentially forget one of the filtrations, and then you get a Z filtered chain complex. So if you forget one of the filtrations in CFK infinity, you get CFK hat. This is a Z filtered chain complex. And well, the total homology of this chain complex, so a Z filtered chain complex gives you a nested collection of subcomplexes indexed by the integers, but you can still just take the homology of the whole thing. This is going to give you HF hat of the ambient manifold, which in this case is just F. And then tau is defining, well, you look for the smallest filtration where the natural inclusion from that filtered subcomplex to the whole thing is surjective on homology. So essentially, you're looking for the filtration level, the first filtration level for which, where this generator for homology of S3 is supported. So tau is the minimum S such that this inclusion is surjective on homology. Okay. And so the way they originally defined tau was for knots in S3. You can generalize the definition to knots in arbitrary integer homology spheres. For an arbitrary integer homology sphere, HF hat might not have rank 1. So instead of looking for the minimum filtration level where this is surjective on homology, you look for the minimum filtration level where this map hits something in HF hat that comes from the tower in HF plus. So that statement was maybe for people who are familiar with Hagar for homology, but basically, for those who aren't familiar with Hagar for homology, you can still, you look for the first filtration level where this hits sort of a special class in HF hat, the one that's sort of related to HF plus. Okay, so you can generalize tau to give us a homomorphism from CZ to the integers. Good. And so I said we were going to use two different concordance invariants coming from knots for homology. So if you've ever seen me give a talk about concordance, you probably can guess what my other concordance invariant that I'm going to use is. So it's this concordance invariant epsilon, which gives us a map from the concordance group to the set -1, 0, 1. So this is not a group, so this is obviously not a homomorphism. Great. So whereas tau only depended on sort of one of the filtrations in CFK infinity, the definition of epsilon depends on both filtrations. So very roughly, the idea of epsilon is you look for you look at one of the filtrations, you look at sort of where the homology is supported, and then you look to see how that sits in the other filtration. Basically, in a chain complex, right, something can be, well, it could be not in the kernel, it could be in the kernel but not the image, or it could be in the image. And those three possibilities correspond to the three different values of epsilon. Okay. So this depends on both filtrations on CFK infinity. And similarly, well, epsilon, the definition of epsilon can be generalized to give you a map from CZ to this set. So you can generalize to give you a map from CZ to here. Okay. So
How do you define that how from CD?
oh, you basically you basically do the same thing. You look for the minimum filtration level, where you look at this map, and then you want to hit something in here such that when you also have this map from CF hat to CF plus. So you look to see when it goes in here, and then you want it to hit something that's in the image of arbitrarily high powers of U. So that's what I meant when I said you want to hit something in HF hat of your three manifold that's like in the image of the tower, like in the image of U in HF plus.
Okay, so do you also get a homomorphism?
Yeah. This tau is also a homomorphism. Yeah, it's maybe a, yeah. I mean, you can show it in a similar way. You just use like the Cournot's formula. It's a little harder than in L space.
Is it the same as the degree of the tower in CFK minus, of the generator of the tower?
Is it the same as the degree? Oh,
Up to a sun.
Is it the same as the degree of? No, it's measuring like the Alexander grading. I guess. Well, to back up, the way I've written things here, we're doing everything. The way what I've written on the board, we're just looking at things that are homology concordant to S3, so D is always 0. But you could do this for any integer homology sphere, and then you basically just want to see like what Alexander filtration do you hit like the bottom. Yeah. But it's different than D, right? Because for like in S3, it's not always 0. Yeah. Other questions?
But I thought, like for in S3, you can also interpret tau in terms of the homological grading in CFK minus on
In CFK.
Or
Oh yeah, and you look at like the things that are the highest thing
yeah,
that's
yeah. So the
non-torsion.
question is it the same in this other?
Oh, I haven't thought about it, but probably. But then maybe you want to shift by D of the ambient manifold, and I haven't thought that through.
Yeah, I guess the question I have is so inside the CF hat you don't have a canonical element. You have a set of a subset of elements.
That's right. So you look for the smallest s, so that you look at this composition, and then you want to hit something that's in the image of arbitrarily high powers of U.
Yeah, so potentially you could have some trouble if you want to prove it's a homomorphism.
Oh.
Yeah, but if you say
it's harder than in like in an L space. Other questions? Okay, so epsilon's not a homomorphism, but you could still ask, well, does it behave in some nice way under connected sum? And it does. It behaves like it's the sign of something. So if you have two knots that both have epsilon equal to 1, well, epsilon of their connected sum is 1, right? Positive plus positive is positive. Similarly, you have two knots with epsilon equal to -1, well, epsilon of their connected sum is -1. And so the important property that we're going to use today is that, well, if you have something that has epsilon equal to 0 and you connect sum it with something else, well, epsilon of the connected sum is going to be epsilon of the something else. So we have the following. And that's going to be the key feature that we'll use. Proposition. So if epsilon of your knot vanishes, then epsilon of that connected sum with something else is epsilon of that something else. And then the second property describes the relationship between epsilon and tau for knots in S3. So if K is a knot in S3, then suppose epsilon is 0, well then tau is also 0. The converse is false. So for example, tau of the 2 - 3 cable of the right-handed trefoil is 0, but epsilon of that knot is 1. So this converse is false. You might wonder what special property about S3 allows us to prove this, and it's the fact that S3 is an L space. So we've sort of seen multiple times this week that like if something's an L space, it sort of says that there's nice things about it. And that's what allows us to prove this. So more generally, if Y is an integer homology sphere L space, then epsilon being 0 implies tau is 0. Great. So basically, right, so epsilon measures some sort of, right, so there's 2 filtrations on CFK infinity. They're often called the horizontal and vertical filtrations. Epsilon measures something about how the horizontal filtration and the vertical filtration relate to each other. And if you're a integer homology sphere L space, well then the homology of like a column is always rank 1. And so the fact that it's rank 1 sort of tells you it's like how when it interacts with say a row, the fact that it's rank 1 sort of tells you that tau of k is equal to negative tau of k, so tau is to be 0. So that's sort of how this falls out. Great. Okay. So we have this nice thing that is true for knots in S3 and presumably not true for knots in other 3 manifolds, and that's what the following proposition says. Proposition. So let J be the 2 - 3 cable of the left-handed trefoil. In case you care, 2 is the longitudinal winding. Okay. So then let Y be, let's do +1 surgery along J, and then let's connect sum that with minus that manifold. Okay. Great, so that's what Y is, and now let me tell you what I'm going to tell you a knot K in Y. So let K, let it be the core of the first surgery. So let K be the core of surgery in here. Okay. Then, okay. The first thing is obvious but worth pointing out, right? So what we connect sum with minus plus 1 surgery along J, so that this manifold bounds a homology ball. So Y bounds a homology ball. Okay, and epsilon of this knot is 0, but tau is non-zero. Tau is -1. So in particular, well, since epsilon and tau are both concordance invariants, this tells us that K is not integer homology concordant to any knot in S3, because a knot in S3, well, if it was concordant to a knot in S3, epsilon being 0 would imply that tau has to be 0. So this gives us something that's non-trivial in the quotient CZ mod phi of C. And now, well, to get infinitely many things in that quotient is now not so difficult, right? Because we know this knot K is going to generate that Z subgroup because we know how tau and epsilon behave under connected sum, right? So we know that epsilon of n copies of this, well, this will still be 0, while tau of n copies of this will be -n. So this implies that this knot K in Y generates a Z subgroup in this quotient. Okay. So now I'll say a few words about how we prove this proposition, right? So one is clear. So to prove 2 and 3, we want to understand, well, C of K infinity for K in Y. And so to do that, well, we do, I guess the way we did it is, there's been mention of this mapping cone formula from C of K infinity of a knot in S3 to the Hager-Fuller homology of surgery along that knot. And in work in progress, Adam Levine and Matt Hedden, well, they generalized that mapping cone formula to be able to give you not just the Hager-Fuller homology of the result of surgery, but actually C of K infinity for the core of that surgery. So for the proof for 2 and 3, we use surgery mapping cone formula due to work in progress of Hedden and Levine, generalizing Oshrat-Szabo. Wait, so this generalization's not written up yet, so we can also prove this using a different tool that isn't written up yet. You can also prove this using bordered minus. Or using bordered HF minus, which is work in progress of Lipschitz, Ajroff, and Thurston. Questions? Yes.
Does tau give genus bounds as well?
Does tau give you genus bounds as well? Presumably, but we haven't proven any of that. But it should, because I think everything in the original proof that tau gives genus bounds should work in. I think it should work in homology. Like, I think it just sort of dependent on the homology of the full manifold. So I think it should all go through, but we haven't done that.
generalization to what?
Oh, right, so, so what would you need? You would need, basically what they do, right, so they have the usual mapping cone formula, and they put a filtration on it. Right, so I mean, what is CFK infinity, like, or, you know, CFK minus? It's a filtration on CF minus. And so, well, the original mapping cone gives you, say, CF minus, and then they put a filtration on it. All right. So that proves the theorem. Wait, so if you're thinking about obstructing, right? So if you think about knots in homology spheres and what obstructions exist to them bounding a disk in a homology ball. Well, there's actually a pi1 obstruction, right? So note. If K in Y is concordant to a knot in S3, then there exists an integer homology ball X, whose boundary is Y, such that K is null homotopic in X. Great. And so maybe, so I'll be honest, so one weakness about this example, right, so we know that this manifold Y bounds integer homology ball, so K is not null homotopic in Y, nor is it null homotopic in the obvious integer homology ball whose boundary is Y. So it could be that this manifold Y bounds, for example, some contractible homology ball, some other homology ball that's contractible, in which case this pi1 obstruction would vanish, but we don't know. So it's unknown. Whether that manifold Y bounds such an integer homology ball X. Right, so you have K sitting in here, such that K is non-zero. Anyway. Okay. So in light of this sort of thing that we don't know about, let me tell you a different way that we know of to construct knots that are not concordant to S3. And so this alternative way relies on d-invariance of surgery. Since d-invariance of surgery don't behave nicely under connected sums of the knots that you're surgerying along, this method doesn't give us a Z subgroup, but it still can give us elements that are non-trivial in this quotient. So we have the following proposition. Okay, so let Y be sigma 2, 3, 13, which is negative 1/2 surgery on the right-handed trefoil. And then let K be the core of surgery. then yk is not concordant to a knot in S3. And wait, and maybe I'll write, and Y bounds contractible co-manifold. This is, I guess, due to the second statement is due to Akvalut and Kirby, I believe. Okay. And so, as I mentioned, this proof relies on D invariance of surgery and which don't behave nicely with respect to connected sum. Of the knots that you're surging along. So let me tell you how we use D invariance to obstruct things from being concordant to a knot in S3. Great. So we're just in the case where Y is an integer homology sphere. So in that case, well, we get D of Y is going to be a even integer. This is an invariant of homology cobordism. Okay, and so the proof of this proposition relies on a few facts about D invariance and homology cobordism. So the first thing to recall is that if K in Y is concordant in homology cobordism to Y, K prime and Y prime, well then, if you do 1 over n surgery along each of them, these are homology cobordant. You can just sort of surgery along the concordance annulus. So in particular, the D invariants of these manifolds have to agree. Wait. Okay. So then we use the following proposition due to Ni and Wu, which says that if you do 1 over n surgery along a knot in S3, where let's say n is positive, well, this is the same as the D invariant of +1 surgery along K, which let's just call this D plus. And similarly, say if you do negative 1 over n surgery, this is D of -1 surgery along K. And let's call that D minus. So what does this proposition say? Well, instead of looking at D invariant of a single surgery, let's look at the set of D invariants for 1 over n surgery. And so what this proposition says is that when you look at that sequence, it can take on at most 3 different values, and it can only change when n goes from -1 to 0 or from 0 to 1. So let's look at the sequence. say for n an integer, right? So it's going to be a bunch of d minuses up until when you get back S3, d is 0. Then it's going to be a bunch of d pluses forever. So this is n is 0, this is n is negative 1, this is n is 1. Right, so this is what happens when you do 1 over n surgery along a knot in S3. So now, well, to prove this, the proof of the proposition, bless you. Okay. Right, so y is negative 1/2 surgery in the right-handed trefoil, k is the chord. So now if you do 1 over n surgery along k, well, this is 1 over n minus 2 surgery on the right-handed trefoil in S3. So in particular, oh, and then you can, let me tell you the d invariance for plus and minus 1 surgery on the right-handed trefoil. So let's call d plus d of plus 1 surgery on the trefoil. This is minus 2. And let's call d minus d of negative 1 surgery on the right-handed trefoil. That's 0. So all we really needed is that one of these be non-zero. So then when you look at the sequence of d invariants for k and y, so it's a sequence of d invariants here. Okay. Well, this thing looks, again, it's going to be a bunch of d minuses, then 0, and then d plus. But now, because of this shift here, right, this 0 happens when n is, this is when n is 2, this is when n is 3, n is 1, right? So in particular, it jumps from 0 to negative 2. Well, if it were concordant to a knot in S3, it could only jump like at 0, where here it's jumping at between 2 and 3. So in particular, this shows that k, this shows that k and y is not concordant. To a knot in S3. So that's all I wanted to tell you about today.
Any questions? Do you know whether S3 plus 1 of J belongs to a homological or an infrahomological?
Do I know? I do not.
The invariance seems to be 0.
What's the d invariant? Actually, I don't remember what it might not be 0. I don't remember. I can check, but I don't, off the top of my head, I don't remember.
Okay, if not, let's go.
Sorry.
What if you pass to like rational homology coordinates?
Oh, what if we pass to rational? So all of the, so you want to look at knots in integer homology spheres?
Yeah.
That bound. So all of the Hayward flow obstructions should still be okay.
Let's type J again.